Right.
So also can join. Just wait. Can I start? Can I start? If you say okay, I can start. Uh,
Yes, sir.
so yeah, or shall I wait for some more time? I think now it is 38.
Yeah.
Yeah, so I think if you don't mind, can you just tell me the topic, last topic covered in the, previous class? I think
Like
session 1
4-bit
or,
full adder,
pardon me?
4-bit full adders and stimulus and all covered.
Okay, yeah, fine.
The
So,
flip-flop.
and I think I have uploaded all the material, of course. Even today's content also I uploaded already. Okay, just go through it. Yeah, I think that full adder is over, right? Yeah,
Yes, sir.
yeah, fine. Okay. Yeah, see, rest of the things are very simple, and I think you can understand. And whenever I come for review, you can ask me if you have any doubts. Okay. Yeah. Yeah, just scrolling and Yeah. I think I was discussing about this, if I'm right. Any doubts here, in terms of stimulus and all that? Yeah, any doubts here? I think this also over. I think my screen is not visible to you, right? Yeah, fine. Uh, yeah, is my screen visible to you? Guys, yeah, please.
Yes, sir.
Yeah, so I think this is what I discussed last class. You remember, or this you want me to repeat? I can repeat. Let's say now, see, this is full add is a module with IOs. Am I audible? Yeah, please. Just I think please make sure my recording is on. If not, please let me know.
It
Yeah,
is on.
yeah. So this is my full add. Full add as IOs. I'm trying to list IOs, and I declare the direction of the input outputs which are mentioned here. Whether sum is output, C out is output. I'm declaring it output sum C out. Input A B C in, and intermediate connections I'm trying to bring in here like wires, and I'm going for gate level. This is gate level description. Whatever I'm just trying to uh, discuss here is gate level description. Just once again I can start. I know I can discuss this, because these things are very important for you, even in terms of let's say, if you look at this line, it gives me this. Probably in synthesis also this is required. If you write like this, let's say output you should write first. My S1 is my output, and inputs I should write later. A, B are inputs here. So next, this line, yeah, please understand. Again, this line accepts same inputs, let's say AB, and it produces C1. Please understand. So it takes same input AB. Next, you go for another XR. See, I go for another XR. See this one. Understand this one. Another XR where sum is output. Please look at it. Sum is output. S1 is one of the input. The S1, which was a wire, that turns out to be one of the input. And C in, it is an external input. So see, this is C in here. S1 is here. It is a wire. This is C underscore in. This gives me this. And again, let's say, and this line gives me R. Understand? This line gives me R. With output C underscore out. This is my primary output. See, this is my output. And C2. See, I think I forgot to mention C2. See, this is, there is one more here I forgot to mention. See, this one, this and C2 S1 C1 gives me this. Let's say there is one more and which is coming here. The output is C2. The inputs are S1. See, this is one of the input. This is one of the input, and C underscore in. This is another input. So this is the output C2. This is the output. I mean, output of this gate and gate output of this gate. But as a module, these two are wires. But if you look at this gate, they are outputs. Okay, now these two outputs, they are wires in this module. They go as inputs to this. Yeah, I think just wait. So see, this is one of the input C1 and another input is C2. This is C2. So this is called as gate level netlist of this module. So when you synthesize this, when this gets synthesized, when this code is synthesized, you get this as synthesized gate level netlist. When this is synthesized, when you fire synthesis, so this turns out to be the gate level netlist. Yes, any doubts here? So now I'm trying to use this as a module in my next level. Okay, I'm trying to use this as module in my next level. Let's say now this turns out to be, now this is one full add. Let's say this is one full adder, this is another full adder, this is another full adder. I have 4 copies of full adder with instance names FA0, FA1, FA2, FA3 respectively. So, and this is my top level full add 4 with corresponding IBOs. Already I have discussed, I'm just briefing it again. It is output 3 down to 0 sum. It is a vector. It's a 4-bit vector. Output Cout, it's a scalar. Again input, it's a 4-bit vector AB. Input Cin, again it's a single bit input. You have wire C1, C2, C3. Now what I try to do here is, let us say, you please clearly understand this. I think those who are working in this domain, they don't need any information on this. Those who are not really working, you please understand. See, what I'm just trying to tell here is, let's say now, let's go for this. Let's say now, please understand. Now, though it is again a repetition, no problem. It's worth repeating it, of course. So, so what I'm trying to do is, let's say I have this one full ladder. Let's say this gives me one full ladder. Let's say I want another copy of the full adder. This gives me another full adder. This is another copy. This gives me another full adder. This is another full adder. So let's say this is sum of this is connected to sum 0 of full add 4. Some of this is connected to sum 1 of full add 4. Some of this is connected to sum 2 of full add 4. Some of this is connected to sum 3 of full add 4. So now understand. The input of this A input, B input, A is connected to A0, B is connected to B0. See, that's written here, B0, this is A0. I'm not able to write here. This is again A1, within square bracket 1. This is B1. Here it is A2, B2, A2, B2. Here it is A3, B3. Here it is A3, B3. Here it is A3, B3. So now C out of this is connected as C into this. Let's say if I call this as C out, it becomes C into this. If I call this as C2, it becomes C into this. If I call this C3, this becomes input to this. Okay, that's what is being shown here. Yeah, any doubts, please feel free to ask me, because you should understand this. So see, this is
Sir,
this. Yeah,
that
please.
scene for FA0, right?
So
what should be the value of that scene?
No, that you can give either 0 or 1. That's under user's control. That's an input, of course. Literally, that is an input. It looks like this. Just say,
3-bit.
let's say,
3-bit. It's a 3-bit.
this one, no?
I mean 4-bit.
No, it is a single bit. Scene is a single bit here. See, this is a single bit. It looks like this. Okay, 1 minute. You just see my slide. I'll go back. There I will tell you. You can understand clearly. 1 minute. See, look at this. See, this is how A, B, C in, right? This is how it is. This is how it is. Yeah, please understand. See, and my scene is available here. Just see, this is my scene. This is my scene. Just see, this is my scene here. So if I go here, see, this is my scene. Is it clear now? For full adder.
Yes, sir. Yes, sir.
Is it visible? Is it clear?
Yes, sir.
See, and again, and in the same line, you understand there is full adder FA1. Again, there is a scene for that, for full adder. It is not written here as a scene. See, that scene is connected to C1 of previous full adder, because carry out of previous full adder goes as carry into the next full adder. That's how the architecture is. Are you able to understand? If you want, I can repeat again.
No, it's
Starting from understood. Okay. The
Yeah.
same thing repeats throughout this. Is it clear? So correspondingly, you have C1, C2, C3 here in place of scene. Let's say this FA1 also has C underscore in, this FA2 also has C underscore in, this FA3 also has C underscore in, but they're all connected to carryouts of previous adder stages. Let us say there is a carryout from this, there is a carryout from this. See, the carryout of this is connected to this, carry into this. Carryout of this is connected to this. Carryout of this is connected to this. Carryout of this is finally C underscore out. See, that is what is being done here. Okay, that's okay. I'll just go back to that now. Okay, see now, this is it. This gives me one copy of full adder, another copy, another copy, another copy. So this is called as port connection by position, but it is not recommended as I said in the last class. This is port connection by position. It's also called as positional mapping. Rather than this, we go for port connection by name. Rather than this, we go for port connection by name. This is something like this. Instead of writing like this, let us say I write the first line, equivalent of the first line. Let's say this is same as this full add. Let's say FA0, same thing, FA0. What I do is dot sum is, let's say SUM is output of full add, this full add. This sum is connected to, please understand, sum 0 of what? Full add 4. Sum 0 of this full add 4, comma, dot C out. I think what was the name given here? Let's say I think C out, ABC in. Okay, C out dot C out of full adder is connected to C1. That's the meaning. C1. This is the syntax, comma, dot A of full add is connected to A0 of full add 4. A0 of full add 4, comma, dot B of full add is connected to B0 of full add 4, comma, C in, comma, dot C underscore in of, please understand, full add is connected to C underscore in of full add 4. Same name, you can use it, comma, dot. Anything else is there? I think I have connected all the ports. You close this and put semicolon. So everywhere,
So,
here also you can repeat the same thing. Yeah, please.
this is the explicit way of connection, right?
Yeah. See, either you can connect like this, but it's not an industry practice, but it is understood by the tools. So, but if you swap the position of these ports, the designer will be in trouble because it does not match the functionality. In case of large designs, it happens. But this is preferred, of course. This is preferred, but the tool understands both. So though the syntax you will have to spend little extra typing time, but it is preferred. Don't even look at it. And again, 2 lines this style and 2 lines this, it is not supported. Completely you have to go for this. Yeah, see, don't try to nest these ways, of course, or these ways of connecting ports. Right? The combination is not supported in general. You will have to go for this. This is recommended, of course. Okay, is it clear now?
Yes, sir.
Yeah. Now,
And this
yeah.
type of code, what we call like a behavioral or gate or something.
Okay, no, 1 minute. This kind of modeling is called as a good doubt. It is structural modeling.
Structural, okay.
Structural modeling. See, generally, if you look at any projects, the RTL code will be structural in nature at the top level, generally, because individual modules are designed and coded separately and they're all connected together. Okay, so this is generally the top level module, okay, or top level representation of any digital system. Yeah, so now let us say
Right.
assume done. Understood?
Sir, I
Yeah,
have
Yes.
one
please.
doubt.
Yeah,
So,
please,
do
please.
we have it is compulsory to first declare output port and then follow the input port
Wha-
sequence, or
yeah, yeah, please.
yeah, or we can first declare the input port, or then
Okay.
we can declare the
Yeah,
output port.
I'll come back to that. See, this is, yes, as you said here, this is called as, yeah, please understand. Yeah, it's a, very good doubt. Yeah, just wait. I'll come back and address your problem. So now, see, this is again, I'll tell you, it is rarely used. It's not very widely used in industry. Yes, it is used. This is called as gate level modeling. What is this called as? Please understand. This is called as gate level modeling. If I use always block to define the behavior, it is called as behavioral modeling. This is called as gate level modeling. I am using gate level primitives. XR is a gate level primitive. And is a gate level primitive. R is a gate level primitive. They are already defined. I'm using them. Got it? When you use gate level primitives which are already available, you need to go for output first, then input. Is this clear? In this mode, yes, you will have to use. But in general, no. If you go for structural, it is your choice. If you go for behavioral, it is your choice. If you go for data flow, it is your choice. You got it? It is your choice. In general, if you go for anything, but if you go for gate level output, you have to write first. That is how the tool understands and interprets. So did I answer your question?
Okay, sir, got it.
Yeah, followed, or still you have any doubt? Please feel free
No,
to
no, no,
ask me.
it's clear. No,
Okay,
no, it's
yeah,
clear. Thank you.
fine,
Yeah.
fine.
Sir, is
Yeah.
structural is also a gate level or
No, the structural can have gate level model inside, of course. Some of the models, okay, I'll just, this is another very good doubt. Okay, I'll just come back. Wait, I will take up 1 minute. What I do, I look for, I think I had one PPT. Now I deleted because I cannot complete all those things. That's why I deleted it. That would have been a good example for you to understand. Okay, fine. Let's say, though I don't have, I will write one more. Let's say, okay, let us say, fine. Yeah, just because next I need to discuss this. That's why I'm keeping here. So now let us say, assume, here you assume, this is my top level, understand. You assume this is my top level. Okay. See, understand, this is my counter. Please understand, this is my counter module. Okay. Understood? No, counter. You counter as a clock, assume. Clock. There is a clock pin for counter. Let's say we give all those things. Let's say. See, this counter, assume the functionality of counter is defined using always. Let's say I define, I'll be discussing this. I'll define the functionality of counter using always. Hence, it is called as behavioral modeling because I'm trying to look at the behavior of this counter. Behavioral modeling. This is called as behavioral. And again, I go for adder here. I go for adder here. This is adder. Please understand. So I write this adder in data flow. You can please understand. I am mixing. You can write in data flow. You can write in behavioral this adder. You can write in structural. You can write in data flow. You can write in switch level, let us say, but switch level is generally not used here. So now let us say the output of this goes as input to this, and again addition happens here. Let's say +1 happens all the time. So this adder gives you the previous count of the counter +1, and again that goes as input here. And again, when you feed one more clock, +1 happens here because you are adding 1 to this. Again, that goes as input here. So now what I am trying to do is, see, this is my top level, let us say. This is my top level. Okay. So, rather than calling this as a counter, you call it as a register. You call this as a register, let's say, okay, register. This top level, let us call it as a counter. Of course, no, it is just a module name, and for understanding, you call it like this. See now, this always goes as an input now. See, this counter as a register inside, and this counter as a adder inside, and these two are connected so that it gives me the functionality of counter. Now, this register is defined in behavioral description, and this adder is defined in data flow description or gate level description. They are connected together. Anything can be connected together. The only thing is every module must have input output ports. If any module has input output port, then they can be connected together. Connection happens only through IO ports. Did I answer your question?
Okay, sir.
You should only have IO ports. That is important. Any kind of modeling style you use, no problem. No problem in general. Okay. Yes.
Yes.
Shall
Yes.
I go ahead?
Yes, sir.
Yeah. So I'll go a little fast. Okay. Yeah, please scope up if you have any
One
doubts.
question.
I think this I have discussed. You remember last class I told you, I remember this, these things. Am I right? I think I told you to take this as an assignment. Yes or no? Implement 16-bit full adder using 4-bit full adder, something like that. Yeah, please tell me yes or no.
Yeah, you told us to do the assignment on this.
This right means previous things I have discussed. Am I right? Yeah, come on.
Yes, sir.
Please respond. Feel free. Okay, don't think it is a class, it's an interaction, of course. Okay, so even I would like to learn from you also.
Hello. Sir, one
Yeah,
question.
am I audible? Yeah, please.
Yeah. So this synthesis, it gives us only the netlist schematic, or it also gives us the physical design?
Pardon me, can you repeat your question?
So when we do the synthesis of this Verilog, it gives us the schematic design, right?
Ah,
So
okay.
does it also give us the physical design of that
No,
module?
see, no. See, when you synthesize, no, is this a question you asked me? When you synthesize this, does
Right.
it give physical design? That's the question, right?
Right.
No, see, what happens is when you fire a synthesis, when you synthesize this RTL code, okay, the netlist is going to be generated. If it is perfectly fine in every sense, if it meets all your PPAs, if it meets your functionality, everything, if it's okay with all corner stuffs, then a netlist is generated. That netlist goes to a PD guy. Hope you're able to understand, right? Then that netlist goes to a
Yes,
physical design
got it.
engineer. So then that physical design engineer will come to know. Just now, if you have seen my previous example, I have taken a counter as top level module. Inside that counter, you have register and adder. Let's say if you look at in that scenario exactly in today's context, if I look at any SOC, you will have, you will have n number of modules. You will have 500, 600 modules. Every module will have a lot of other modules inside. They're all, wrapped together. Wrap up happens there depending on the functionality. They're all wrapped inside another. So what happens is when you synthesize, right? So what kind of gates or what kind of netlist is what kind of netlist which is really required to meet your design constraint is going to be generated, and just by looking at it, a PD guy will try to place it, and he will try to route a signal from one module to another module, or from one cell to another cell. He will try to see, and he will try to optimize so that it's going to occupy lesser silicon space or lesser silicon real estate, and it gets optimized with respect to speed. He looks at that, of course. Is this clear? That PD guy
Yes,
will
yes.
have to look at it. But when when we fire a synthesis, we don't get PD out of it, of course. You got it? We get a netlist. That netlist goes to a PD guy. Again, when once he finishes his job, again he will get a netlist. Are you able to understand? The job is only with
Yes.
respect to netlist now. Is this clear?
Yes.
Okay, fine. Yeah. So now
Sir,
look.
I want
Yeah.
to add one more thing here.
Yeah.
So if synthesis has a two types, logical and physical. So if we giving the physical input, like as I work, I'm working. So if I doing the floor plan and if I'm giving the input on synthesis, so whatever the synthesized netlist I will get, it is a physical like a design already done. On based on that, I will getting my result. So we can say that if we are doing the physical synthesis, then we will get the physical netlist. But if we are doing the logical synthesis, you are not doing any placement, or if you are directly giving, then you will get the with while load model you are getting the result.
Sure, sure. Yeah. Definitely. Yeah. You are right, of course. No, but I'm just talking only in this context. Yeah.
I
Fine.
just
No.
want to add this.
Yeah. Fine. Thank you. Yeah. So now let's see. I want to bring in the behavior of a D flip flop. Let us say. So it could be, let us say, if reset is 1, my Q must be initialized to 0, else whatever D I give, that turns out to be my Q. That turns out to be my Q. So let's see now, this is what is called as, any guess? What kind of modeling is this? Just now, may I know your name? Just now someone said something. May I know your name? I did not notice. Let's see now. Just see. So what I'm trying to do now, let's say I have this functionality. Let's say I'm trying to trigger this guy using clock CLK. Okay. So let's say
behavioral modeling.
Absolutely. Yeah, that's what I just would like to. This is no doubt. Okay, let's say I have input D, okay, and this is output Q. So what this guy is doing, I'm trying to define this architecture somewhere inside this always what this is doing. I'm trying to define somewhere inside this always. Okay, see the functionality or how this design looks like. So see, the question here is, please try to understand. So I'm trying to update the value of Q inside always. Just see, Q is getting updated inside always. That is why I need to declare this as, by default, no doubt I need to declare this as output. But in addition to output, I need to declare it as ridge Q. You can go for single line or you can go for 2 lines, of course. See, output by default, even if it is a module without always, you need to go for output. But when you try updating it inside always, mandatorily you need to go for ridge. Mandatorily in Verilog. Again, there are scenarios, of course. So you need to go for ridge. Anything you update inside always must be declared as ridge. This ridge is this ridge when it gets synthesized, does it really gives you hardware register? Any guess, people who are working? Does
No.
it gives me hardware register in all the time? See, now you see, depending on the scenario, let us say if you are really looking at sequential purpose behind this, of course, may give you a register, but not all the time, of course. But in general, this ridge does not mean it is a hardware register. It is just used to store the data, right? It is not hardware register. Okay, it is just used to store this value for some time depending on the requirement. Let's say if reset is 1, my Q is 0 because it is my passage reset. But generally the industry assumption is reset should always be negate. You can negate, because this is taken from some reference. So that's why I've used in books. You will see these kinds of definitions, of course, but it is opposite. It is reverse. Clock is always passage because I need to give you some reference with respect to book. That's why I'm looking at it. So clock must always be passage in general, of course, but logically I don't see any difference. Negate also works. Okay. So there are inputs like D, this is input D, and there is input clock, and there is input reset. There is input reset. Now, see, I'm trying to define the behavior of this using always. Any guess what does always mean? Yes. Yeah, please feel free. Any guess what does always mean here in this context? What exactly is always?
Sir, on every positive of reset or every negative of flow. Every.
No, yeah, that is right. No, what exactly is the meaning of always here?
Every time.
Every time, yes. No, it is basically, let us say, I just would like to bring in a scenario, let's say, because if you look at a combinational circuit, we do say combinational circuit is active as long as clock is delivered to it. Got it? Combinational circuit will be active, sorry, sequential circuit will be active as long as clock is delivered to it. Now let us say, if I want to trigger any logic with respect to a clock, let's say, here always is mandatory. Without always, you cannot use clock at all. So, because to make a circuit active all the time, let's say, generally we are under the impression that clock is required. So to use a feature which is all the time available with a circuit, right? We need to look at a syntax which is always, okay? It is always. So that is why in order to use this kind of signals all the time, we use something like always. It is more or less like infinite loop in C. So, and again, what I expected from you is, it is always is more specifically in digital context, always is used to represent continuous activity in a digital circuit. This is what is expected. Always is used to represent continuous activity in a digital circuit. So let us say, what is this continuous activity? The activity will be continuous, let us say, as long as clock is applied, as long as clock is available, the activity will be continuous. So now, without always, you cannot even think of clock. If you really want to use clock, in Verilog, you should always go for always. People who are working in this domain, others, yeah, please understand. Don't try to drive something without using always, it doesn't work. So, but see, the other way of looking at it is, you can build, if you look at a digital circuit as a whole, 1 minute, if you look at digital circuit as a whole, you have two types of circuits. One is combinational and another is sequential. So you can build combinational and sequential using always. Using always, you can build combinational circuits and sequential circuits in Verilog. I'm talking about. In Verilog, I'm talking about. But you cannot build sequential without always, but you can build combinational without always. Always is mandatory for, it's for beginners, of course. It is mandatory for sequential, but in general, you can build combinational without always also, but with always also you can do, without always, without and with always you can build, without and with always you can build combinational logic. But to build sequential logic, always is very much important and mandatory, of course. Okay. So now, now let us say, see, this is what is my D flip-flop. Please understand. So what I do is I just go back. See now here. So let me just understand this. Very interesting behavior, of course, and not difficult at all. I think, which is okay, fine. Yeah, let
Sir, I have one doubt.
Yeah,
So
yeah.
after always, is it required to define the condition positive edge or negative edge?
Where, which example you are talking about? Previous one?
Yes, yes.
1 minute, 1 minute. Just I'll go. Just let me know. Is this, yeah, this one here?
Yeah,
This one, huh?
always you just explain.
Always
Yes.
at passage. Yeah, this is mandatory. This
Okay.
is mandatory. This is called a sensitivity list. So
Okay.
all this behavior, whatever I have written here, is sensitive to this. Let's say if you have reset 1, immediately it will give my Q0. You got it? So
Okay.
if you have negative edge of the clock, right, then only these things will happen. Only your data transfer happens during negative edge. If you really want to have that kind of behavior from a sequential circuit, you need to go for this neg edge clock, right? If you don't,
Yes.
you need to write it. Okay, this is more specifically called as sensitivity list, because entire functionality, whatever I write inside this always is sensitive to these signals. Is sensitive to these signals. These signals are written inside this bracket, and these signals are collectively called as, right, this,
Okay.
the set of all these signals is collectively called as sensitivity list. Okay,
Okay.
so
So
you can have, yeah.
if we not define the sensitivity list, can we say that a sequential element will be behave like a synchronous
See,
element?
see, one thing is, let us say if you have purely combinational, some generally tools will support if you put star. Okay,
Okay.
it
Okay.
it by default understands in some scenario. There are some limitations there. If you put star, see,
Okay.
today's synthesis tools will understand as if though you do not mention all the signals which are really sensitive for this, they understand as if they are all available and sitting inside the sensitivity list. But if you really
Okay.
don't want to take any risk, you can mention them, of course.
Then
But
it
when you
will
have,
consider as a synchronous element, right?
now that the asynchronous, you can handle it differently. This is, yeah, this you can handle it differently. That's a different scenario, of course. Okay,
Okay.
so here
So
it
here,
is. Yeah,
okay, here, so
see,
for asynchronous, here we
it
no
is,
need to play anything, right?
no, here it is asynchronous reset here, because it doesn't even look at whether my clock transition is happening or not. The moment passage reset happens, it will be reset to 0. Okay, it is
Okay.
asynchronous reset. If you remove this passage reset here, if you put only negate clock, it becomes synchronous reset. So even if reset changes somewhere other than the negative edge of the clock, it does not look for it. If the reset changes during neg edge clock, then only it looks at these transitions. Okay, so
Okay.
means my reset is getting synchronized with respect to negative edge of the clock, hence it is called as synchronous reset. No, that's how you can drive it, of course, depending on the requirement. Always
Okay.
synchronous is better, of course, because this is, I'm looking at the Verilog part. I'm just trying to teach both, of course. Okay,
Okay. Okay. Got it.
there are a
Yeah.
lot of
Thank you.
guidelines, and the tool also knows. It will just tell you, you do like this, something like that. Based on that, you can tweak it, of course. Okay,
Okay. Got it. Yeah.
yeah,
Thank
fine,
you.
fine. Yeah, bye. So now look at it now. Yeah, this is quite interesting behavior. Please understand, it's not difficult, very simple. I have a lot of things to, 1 minute. I'll have to capture everything. Look at this. Okay, so this is now my top level is, yeah, please understand, this is my top level. Please understand now. What is my top level? Let us say T underscore FF, I call it as my top level. Okay, see, all the naming conventions are not like industry. Of course, you go for meaningful names for IOs, YS and all, helps a lot, of course. Okay, see now. So already I have a module for DFF previously. I bring in that DFF guy here. That DFF, I think D underscore FF, something like this, right? D underscore FF is already available to me. We have seen in the previous case. This DFF and inverter, let us say. This inverter is also there. Inverter, let us say. See, these two are connected together. Please understand. These two are connected together. Okay, the output of this is connected as input to this. Okay, and the output of this is connected as input to this. Got it? Right? And this is my final output from, let us say, D flip-flop. So now what I'm trying to do, I'm trying to connect D underscore FF and inverter together here. Right? So again, this is a structural description of T underscore FF. Yeah, you please understand here, see, for this TFF, let us say Q is the output, and clock is the input, clock is input, and reset is input. Clock is input, reset is input. Clock is input, reset is input here. Now let us say already this DFF is available. This is a placeholder for the previous functionality. You hope it is clear, right? See, this D underscore FF is a placeholder for the D flip-flop functionality which already I have defined. I need not have to write all the lines again. I just write same module name. This module name must be same. This is the instance name. I plug in this port mapping. You can do like this, or you can do dot Q is connected to Q the way I said, and dot D is connected to D, comma, dot CLK is connected to CLK, comma, dot reset is connected to reset. Something like this. You need to do it. Okay. So now, is there any doubt here up to this? Yeah, please. Because this is very important to understand the concept. No, even if you go for any complex design, only thing is your IOs are more and number of modules are more. The number of modules you are trying to connect them together, you will see more such modules, but the concept remains same. Even if you jump to SV, it remains like this only, of course. Okay, so now what I do is, so this inverter, you can write a separate module for this. So here separate module is not written. You can write a separate module. See, what has been done here is, no, it is just, I have just used a primitive, gate level primitive we have used here. Gate level primitive has been used here. Gate level primitive is used here. See, now let us say this Q goes as input to this inverter. This Q goes as input to this inverter. See, I'm writing this. Am I audible to you? Hello? Hello? Am I audible to you? Guys?
Yes, sir, it is audible.
Yes.
Okay, screen is visible to you perfectly
Yes,
fine?
it is visible.
Because I have
Yeah.
got some message. Yeah, fine. So now look at this NOT. Look at this NOT. NOT is a gate level primitive. No, see, it is not mandatory to go for this. It is your wish. This is one such possibility. That's all. I am not really restricting your thinking process. You can use anything. Okay, but here, this is one possibility that also gives me this behavior. That's all I'm trying to tell you. So this NOT, what is the input to this NOT? Q of this is input. Let's say this is Q. What is Q? Q is the output of this DFF, right? And that goes as input, and this D is the output of this inverter. This I am declaring it as wire. See, the same D is connected as input to this D flip-flop. Please understand, the same wire D is connected as input to this D flip-flop. So this D is connected as input to this D flip-flop. So now together, can I say this is a T flip-flop? This is the simplest model of T flip-flop. Okay, so this is T flip-flop. So now hope you know, I defined D flip-flop behaviorally and I connected it with inverter. That defines a top level module T underscore FF. Now what I do, I use these 4 T flip-flops. I use 4
So
T
why is it
flip-flops.
called DFF0? Like any
Yeah,
particular reason
no,
for
no,
it?
yeah, 1 minute. I'll just, I'll come back. No, there is no reason. See, this is an instance name. So it is something like this. Let us say I have 4 Kartiks in a class. I have 4 Kartiks. I want to address one Kartik. If I say Kartik, let's say all may respond. I don't want this to happen. Let's say Instead of that, assume all Kartiks have names. Kartik A, Kartik B, Kartik C, Kartik D. Let's say if I want to talk to Kartik C, I can directly say Kartik C, this is for you. This is just that. This is just that. DFF0. Okay. So again, I want to go for another instance. I can DFF, I can write, that is there in the next example. Wait, DFF, I can write it as DFF1. Means you should go for unique name here. Again, I should not use DFF0 because if I want to address this DFF, functionality is same, but as far as the behavior and porting, it may be different. You got it? So I can say, I cannot say DFF because all are DFFs only. Are you able to understand in terms of functionality? All are D flip-flops, but this is DFF0 and this is DFF1. It becomes easy to address it, of course. Only that is the difference. Okay. Yeah.
Okay.
Yeah. Now, so now what I do,
Sir,
yeah.
why is Q not declared as wire here? Since it is an input to the NOT gate.
Fine. Yeah, it's a valid question. The question is, am I updating Q here in this top level? Am I updating Q inside the always block? If I update this Q inside the always block, definitely it should be registered. Am I doing it here? Yeah, please think. I'm not updating in this top level. Yes, I updated in previous module. You are absolutely right there. But here I have not updated inside always. Hope it is clear to you, right?
So if Q has to be declared as wire or register, it should be updated inside always.
Yes, absolutely. Yes, that's what Verilog says. Absolutely. See, and generally, what designers were doing before, okay? There was a lot of confusion between wire and register. Sometimes no, because we all, sometimes in place of wire, if you declare ridge, it used to throw a lot of errors, and the functionality also could differ in some of the cases. So this was the problem, designers were facing, because you have millions of lines of code. In place of ridge, if you declare it as a wire, gone, because you will have to rework, and you'll have to spend too much of bandwidth on it. That is why I think in the next revision, right, they try to avoid this, and they defined a new type of logic called as logic. That itself is logic. There, even if you swap this wire ridge, that's not a problem. That logic is a new type which is defined in SV. You need not to worry too much about wire ridge. No, but wire ridge is supported, but you can simply declare it as logic. That's in SV. Of course, SV is emerging as a very good synthesis language now. Before and now also, it's a very good language for verification. But now it's emerging as a powerful synthesis language as well. Many companies are into, RTL design using SV now. Okay. Yeah, fine. Did I answer your question?
Yeah, sir. So one more
Fine.
question. So if
Okay.
here we do not declare wire D, will there be a problem?
Definitely, because this is an interconnection, right? See this, look at it. Yeah, 1 minute. This is a nice question. 1 minute. I am also bit. Yeah, wait. Sudden transition. Fine. Let's say now you look at it. Very valid question. Yeah, just see. Now let's say I want to feed this back to this, right? I want to feed. Let's say this guy is available to me like this. Okay. This is, yeah, of course. Let's say this is my D. This is my wire D. This is my wire D. This is my Q. Now, let's say this DFF is sitting here. This is my DFF. So again, this is my D. Got it? It looks like this now to us. Yes or no? Now I want to put one connection. No, physically, if I give you these two, inverter and DFF, how do you do it? You put one wire here, right? That's how it is.
Yes, sir.
I need to have a wire in a language also. No, that is why Verilog uses same thing like wire. I think VHDL, there is another language called VHDL. I think if I am right, that uses something like signal, but here it is a wire, right? And if you move slowly to SV, it is a wire. It can be declared as a wire also, but you can directly declare it as logic. You can directly declare it as logic, no problem at all. Are you able to understand? Clear? So if you really want to have this kind of connection here, you need to go for this wire. Otherwise, it will throw an error. Okay.
You will have to tell, just look at this connection. Otherwise, your functionality will not match. Okay, fine. Shall I?
Sir, in that
Ah,
logic, Q should
okay.
also be declared as a wire, no, sir, because
Where
it is
you,
going.
no. Yeah. See, by default, they are wires only. Even if you declare, no problem. Okay.
Okay.
Yeah.
Okay.
By default, because all default things I'm not discussing much. Okay.
Okay, sir.
Okay. Fine. Did I answer your question? Okay.
Sir.
Okay.
Sir, I have
Yeah.
a doubt.
Yeah, please.
Sir, in Verilog, are we allowed to declare wire in the RTL? Like we have practiced like declaring a wire in the test bench only. In the RTL, can we declare
No.
it?
You can. Otherwise, how can you model it? You cannot model it without wires. It's
But sir,
required. It's
usually
supported. No. It is. Yeah. Tell me.
in behavioral modeling, we usually declare reg. Whatever input is there, whichever is required to be declared as reg, we'll declare it as reg. But I have never seen like declaring a wire inside the RTL.
No.
Wire was just
No.
used in the test bench, so I had a doubt.
No. Wire by default, it is supported, of course. Even if you don't mention explicitly by default, all IOs are wires only by default. Okay.
Okay,
No,
sir.
output Q is a wire. Even if you write it as output Q wire, no problem. It takes it. It reads it properly. And all inputs are wires by default. That is why probably you are not explicitly declaring it, but they are by default wires. No doubt. It is supported. No doubt it is supported. And in as you said, in verification environment also it is supported. Okay.
Okay, sir.
Yes. Okay.
Thank
Now,
you, sir.
yeah. Bye. So now, wait. Okay. Look at this. I had one separate diagram. Let me see. What I do. Okay, fine. Let me not spend most of my time here. Let's say, yeah, I go for this. It is in reverse order, of course, but kept in this order for some purpose. But you understand everything which is really required for you to understand is sitting here, of course. Okay. Now see, yeah. Now what I am doing is, look at it. I'm trying to build ripple carry counter. Oh, I think so. It is asynchronous by definition. Let's say you have 4 T flip-flops. Please understand. You have 4 T flip-flops. Okay. You have every T flip-flop as a reset. So I write it as R for understanding, because writing reset takes a lot of time. So this is reset. Okay. So see, this is my top level. Please understand. This is my top level. See, this top level as this reset. Guys, please understand, this top level as this reset. See, these individual resets, look at it in this place. They're all connected together to the same reset. Yeah, this is how it is. This is how it looks like. Now, I understand this is a clock pin. You please understand this is my clock pin. So I am providing, this is my clock of, asynchronous counter, right? See, this is connected to this. And let's say I have Q of 0, this one, Q of 0. Let's say again, this is clock of this clock. This Q of 0 is connected as a clock. Again, I have Q of 1 here. Please understand. Again, I have a Q of 1 here. This is clock here. This is clock here. Again, this Q of 1 is connected as a clock to this. Again, this is Q of 2. Again, this is Q of 2. Again, it is connected as a clock. It is connected as a clock here. So see, this is again Q of 0. You can use it as output. This is your Q of 0 output. This Q of 1 is output. Q of 2 is output. Q of 3 is also output. You got it now? This is how it works. Now understand here. Just I delete. If you have any doubts, you please ask me now. Okay, now. So see, this Q of 0 goes as clock to the next flip-flop. This Q of 0, look at it. This Q of 0 is a clock, right? Is a clock, because in place of clock I have this. So the master clock is hitting the first flip-flop. Okay. So now what is the output produced by this Q of 1? This Q of 1 acts as a clock for this. So it produces Q of 2. This Q of 2 acts as a clock to this. So the other way of writing this is, if you want, let us say, so I need to look at this. I need to look at the names Q clock reset. Okay, look at this. It is Q. Please understand Q clock reset. One line I will write Q clock reset. These are all ports with respect to T underscore FF. This line you can write it. I assume I make it a comment. This line I write it as T underscore FF. So I can discuss these things in lab, of course. Couple of flip-flops I can discuss. See, TFF0, TFF0, I can write like this. Please understand dot Q of T underscore FF is connected to Q0 of ripple underscore carry counter. This is how you can tell the tool. Yeah, look at this Q0, comma. Now dot clock of T underscore FF is connected to CLK of ripple carry counter, comma. So you continue the next line. So I don't have space, comma, dot. Next, reset. See, what I'm writing is reset of T underscore FF. Please listen carefully. T underscore reset. Reset of T underscore FF is connected to reset of ripple carry counter. See, whatever I am trying to write inside this bracket, close this bracket. This bracket I'm closing here. See, whatever I am writing inside the bracket, they are all with respect to top level module. Please understand. This is important. They are all with respect to top level module. Whatever I am not writing inside the bracket, they are all with respect to this lower level module. Lower level module is TFF. This is clock. This is reset. Yeah. So is this clear? Come on, tell me. Tell me.
Means if we have a less number of flip-flops or less number of blocks, we can use the explicit way of connection.
No, yeah, no, there are various ways, yeah, I'm not really looking at it. Yes, you are absolutely right. No, as far as instantiation you are talking about, no, there are
Yes, sir.
something like generate. Yeah, you can use them. Absolutely, no doubt. Because
Means if we
similar,
have more number of things to declare, it is
correct.
difficult to call it name.
Definitely you can do it. That option is there, no, because our focus is something else. That's why, I'm just trying to touch upon these topics. That's it. Yeah, definitely
Yes.
you can go for generate and all that options. Yes,
Yes.
you have it, of course, no doubt. Yeah, fine. So now let us say, see, now the question is, my ripple carry counter is available to me now. Ripple carry counter is available to me. Now I will have to verify it, whether it is meeting my requirement or not. Just see. See, what I am doing is, just look at it. A very simple test bench with some test scenarios. Is it visible to you clearly? Clearly visible to you? Yeah, it's a very simple and nice example for you to understand as a beginner, of course, not for experienced guys, of course. Okay, now let's say I write module stimulus. This is again in Verilog. Okay, fine. I still wanted to have it. Yeah, just let me. Okay, now this is a module stimulus. Now I think clock reset are inputs in my asynchronous counter, right? Asynchronous counter or ripple counter, yes or no? So this is my ripple counter. So one thing, let us say, what is the name which is being used here? Same name I should use. Okay, here I'll have to use ripple carry counter. See, ripple carry counter I should use. Yeah, please understand here. Ripple, see this name, this name you please make a correction according to this, or else ripple underscore counter. For me it is easy to change here. Ripple underscore counter. You don't write carry here. That's it. Now this is perfectly fine. Save it. Okay. See, this is ripple carry counter. Name change doesn't happen. Sorry, name change doesn't make any difference here. Okay, name change doesn't make any difference here. Ripple counter, why I changed it? Because I know a ripple underscore counter is used here. So same name must be here also. Ripple underscore counter. Only that is the reason. Okay, nothing else. See now, this is a DUT now which we are trying to verify. This is my design and the test. Okay. So now which are the inputs required to test this ripple counter? If you look at this, which are the inputs required? Clock reset are the inputs required. Q is the output. Q is the output. So now look at this. So inputs are declared as registers, output is a wire. So now see, this is connection by position. You can see dot Q is connected to Q, clock is connected to clock, reset is connected to reset. Now there are two procedural blocks in Verilog. Yeah. Any doubt? Yeah, there are two procedural blocks in Verilog.
Do we need to give input as well, right?
Pardon me, can you be a bit louder? Your voice is
Yeah.
bit.
Here, do we need to give input as well, right? Ripple counter.
Input?
Yes.
Pardon me,
Like,
can you?
do we need to define any input for a ripple
No.
counter?
Yeah. Sorry, one thing. No, see, this is a test bench. Test bench will not require inputs and outputs. It is just, this is just to verify, because this does not go and sit inside silicon. So, it does not require inputs and outputs. Test bench
For
does not
any
require
test bench,
inputs.
we don't need to define
No, does not require IOs, inputs and outputs, but you will have to manage them as registers and wires, of course. Here. Okay. Yeah. Fine. So, so now, okay. So Verilog has two important procedural blocks. One is initial. Please understand. The another one we have already seen, always. Always is continuous, but initial is, it gets executed only once during the entire simulation. Execution is only once during the entire simulation. See here, the execution is continuous. So these two are important procedural blocks. These two are important procedural blocks in Verilog. They are important procedural blocks in Verilog. Okay, fine. So now what I do is, so see, initially I declare clock 0. Initially, let's say my clock is 0 here. My clock is 0. So now I use always here, right? So after every 5 time units, my clock is becoming not of clock. Yeah, please understand. So I'm trying to generate this scenario here. This is 5 time unit. This is 5 time unit. The clock period turns out to be 10 time unit. Again, this is 5 time unit. This is 5 time unit. It repeats again. So I'm just looking at, I think, positive edge of the clock, right? So it turns out to be this. My event should really happen here. So then only I can, it gets sampled properly. So now, so this is what is continuously happening here. So this 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0 is continuously happening here. So now let us say what I do, reset I give 1 in the beginning. Okay, I give reset 1 in the beginning. After 15 time units, reset I make it 0. If reset is made 0, please understand, if the reset is made 0, okay, if the reset is made 0, at what time I'm making reset 0? At 15. But definitely from 15 to let us say 180, means from 0, if you look from 0, it is 180 plus 15, it looks to be 195. From 15 it looks like 180, but if you look at from 0, it looks like 15 plus 180 is 195. So from 15 to 185, look at it, according to this test scenario, my reset becomes 0. My reset becomes 0. Understood? So now, yeah, please understand. Now at 195, please understand, at 195. So from 15 to 195, my reset is 0. But according to this, at 195, I make my reset 1. Please understand. At 195, I make my reset 1. See, at 190, yeah, please understand now. At 190, what is the value of my reset? Yeah, please. What is the value of my reset? Come on. I
0.
want you, yeah, 0. So if reset is 0, it works as a counter. No, according to my specification. Okay. So now if reset is 0, it should count. Let's say the previous count was 1, it becomes 2. Now let's say at 195, what I am doing? No, at 195, I am generating reset 1. So see, now my counting is 2. The moment reset becomes 1, no, my Q becomes 0. Are you able to understand? I am trying to test. Even in between, if I make my reset 0, is it really coming back to Q0? That's what I'm trying to test in between. Like this, you can test wherever you want. This is one scenario I'm trying to highlight. Is this clear? Now it is 0. Yeah, please understand. Now immediately, let's say I'm making 0. Now at 195, I'm making 0. After another 10. After another 10 means what? At 205, please understand. At 205, again I am making my reset what? Come on, what? I am making my reset 0. See, at 205, somewhere here, I make my reset 0. If my reset is made 0, it should count again. See, at 205, the next captured event here is at 210. It becomes 1 now because my reset is 0. Again, it will continue at 20. After another 20 means at 225 dollar finish. Somewhere here, I'm completing my simulation and I'm capturing, the event at 220. At 220, my reset is 0. It counts. So if you, let us say, if you make it another 50 here in place of, against my dollar finish, you will see some more counting sequences. But I'm stopping this. I'm finishing my simulation at this point of time. So now what you need to understand is, depending on your requirement, you need to generate all these test cases. See, from here, from 15 to 195, from 15 somewhere here to 195. So here 195, my reset is 0.
Sir,
So as
how
reset is
that
0, yeah.
how that timing incremented from 0, 10, 20,
No,
30,
yeah,
only
yeah,
10.
yeah. No. See, my clock is this, no? Clock. This is with respect to clock timing. See, this is 0. I'm printing this, that's all. I'm printing it 0, 1, 0, 1. This is, the period is 10 here. You have 10 here. Okay. This is it. You have 20 here. See, you have 20 here. See, here this I have printed 20. You can write at 10 also, no problem. This becomes 30. This instant becomes 30. Like this it is printed.
Means we declared 10 as a period.
Yes, because clock becomes not of clock after every 5 years. I declared it. If you want, you can change it. It's your wish. Okay. But there should be a meaning behind this also, of course. I'm declaring it as 10. That serves my purpose, of course. I can look at all this. Okay.
How this
Clear?
count is 15 till 160, and after that it is switching between 1012, 012.
Okay. So just say, yeah, just listen carefully. So what is your doubt? Can you repeat again? Yeah, a bit louder,
So
please.
the value of Q output is 15 till 160, but after that
correct,
it is switching between 012, 012.
correct.
Right?
Yeah, fine. Yeah, that's a good question. 150 at 160 still, what is my reset? At 160, what is my reset? Come on. Yeah. Reset is 0, right?
0.
Now let us say I have reached maximum value, but I'm adding 1 again to it, of course. What is this? 0 with a carry out of 1, 0 with a carry out of 1. It is addition. 0 with a carry out of 1, 0. There is this, but I'm not capturing. If you want, you can capture this as well. Then it will not be 0, it will be 16. That's it, because I'm capturing 0. It wraps around. It is wrapping now. Again, I'm adding 1 to it. It becomes 001. It is just only because of this. I'm not capturing this MSB. That's it. Got it? That's, that's a good observation, no doubt.
But this ripple counter is not initialized inside the always block. Yeah, so even if it is get triggered at the simulation, it will be executed only once, right?
No, 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 no.
Okay.
See, no. See, the signal clock is initialized. Clock is initialized as 0 in the beginning. Okay. See, initially to start with, I should have some value for clock, no? Otherwise, let's say if I don't declare something unknown, if it gets initialized too, I do not know how to find a complement of unknown, or how to, how to look at not of unknown, it is not defined. That's
So
why always we should.
we can say this ripple counter works for the complete cycle of the reset and clock till the time
Yes,
is not there.
yes. That is what
Okay,
I'm trying to verify. We are trying to
okay.
verify. No, and again, here also you can make reset 1, and you see whether it goes back to 0 state or not. You can do that. You can try out. Definitely. And okay, did I answer your question?
Yes, sir.
Yeah. See, and another, let's say, yeah, see this one, good observation, good interaction. See, these things you please see. This is just because of this monitor. Yeah, this monitor is like, I think you have seen printf in C. This is just because of this. See, and more specifically, this time, dollar time, this gives you this timing information. This dollar time will give you this timing information. See, and output, let's say whatever you keep inside this double bracket, sorry, double quote, whatever you write inside double quote, this is output Q equal to %D. This is a decimal format I'm trying to print. This is a decimal format. Decimal format. This is Q. What is this Q? This is this Q. This is this Q is sitting here. Of course, I'm trying to print this Q. So output Q equal to %D, that is Q. Are you able to understand? So dollar monitor, if you see this entire thing, please understand this entire thing is because of this dollar monitor.
Yes, sir, understood.
But it's in simulation environment. That's all. Are you able to understand? This
Yes.
is dollar monitor is not supported for synthesis. Of course, we don't want to synthesize this behavior. Just because before I get a final netlist, I should see whether it meets my rec or not. Otherwise, no point in going for rest of the processes. Okay, got it? So I think yeah, please let me know. Is this clear?
Yes,
So then I can
yes,
move on to other topic. Okay.
yes, sir.
Fine. Yeah. Let's see. I think I have done with this. Okay. Now the job for you is. Now what do you need to do? Yeah, you will have to think about it, of course, and it improves your digital design concepts as well. Okay, see, you have seen the implementation using T flip-flop, yes or no? Okay, so now what do you have to do? You have to look at 4-bit asynchronous down counter using negative edge trigger D flip-flop. You have to implement 4-bit asynchronous up counter using positive edge trigger D flip-flops. You have to implement 4-bit asynchronous down counter using negative edge trigger JK flip-flops. Please understand. You should implement 4-bit asynchronous up counter using positive edge trigger JK flip-flop. Look at it. One is down and another is up. You just see, right? How to go about it. Okay, it helps you. Okay. Now, I think I will have, yeah. So we will go for some sequence detectors, finite state machines. Okay, let's say now some coding issues. Let me try to take up. Okay, fine. Let's say this is what already I've discussed. This is a event list. Okay. This is pipeline registers. Let's just go for this. Okay, just see. Now, assume this. Fine. See, don't worry about this index. It is written as -8. So now let's say output reach signed 5 down to -8 average. Don't worry. You can. It doesn't mean that you should go for -8. Okay. It's up to you, but you need to look at right number of bits. Input signed 5 down to -8 ABC input clock. So what I want, there is some concept like pipelining. Just would like to tell you about it. Okay. See, this is pipelining. Let's say you have a combinational logic, combinational logic, combinational logic. I try to break it. Let's say. So I insert this D flip flop in between. I insert this D flip flop in between and I trigger by a clock. This is my D in. So now what is the clock period now? It is maximum of the delay generated by combinational circuit 1, combinational circuit 2, combinational circuit 3. What is total delay? See, the total delay is 3 times the clock period. Okay. Now, so see, let's say now I declare some intermediate signals A plus B, some div 3. So, you know, and I declare one register. I think 3 registers. I think 3 registers are required. Saved A plus B, saved C, saved some. See, this -8, you don't worry. You can go for, 10 down to something like that. It is your wish. Now, let's say now, let us, okay, fine, understand what I am trying to do now. Let's say a complete code is not written here. Let us see now. I am trying to add, okay, some numbers, let us say. So what I do, I first add A plus B. You please understand. I'm trying to add A plus B now. I'm adding A plus B. 1 minute.
Sir, can
Yeah.
you clarify that 5 minus 8, that range, what is indicating?
No, that is, yeah, 5, 5, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, like that. It is used to represent the width or the size of the operands. Okay. That's why I said you can change it as well. It doesn't mean that you should go to minus, minus also. If it is supported, you can use it. Yes. You can.
It's going back 5 to -8.
Yes. Back. Yes, absolutely. You can look at that index as well. Just 1 minute. Okay, just see. I don't know why it's coming like this. Yeah, just see this. See now, first I do A plus B. A plus B is assigned to, let's say, A underscore plus B. Yeah, please understand. Now, what I do is, yeah, you please understand. So now I declare another one, what it is supposed to be now. Yeah, please let me know what it is supposed to be. Is it supposed to be a ridge here? Yeah, please understand. Saved underscore A underscore plus. What I do, I assign it to A plus B. Yeah, please understand. And again, there is one more input. I assign this C to saved underscore C. It is one possible scenario, of course. So now what I do is I go for pure combinational logic. I add these two. What I do, I add this and I add saved underscore C. See, saved underscore A plus saved underscore C. Okay, now at positive edge of the clock, what I am doing, let's say sum takes the value of saved underscore A plus saved underscore C. Now this sum is assigned to saved underscore sum, right? So in the next clock pulse. Okay, so and again, I am, see, this is what is being done is, let's say I'm trying to find the average. Okay, average. So that average is, I think average of 3 numbers, let's say it is sum by 3. It is sum by 3. It is 1 by 3. You can write it as 1 by 3 into sum. That's what is being done here. So this is saved sum, and this is, this is the representation of 1 by 3. You can check this. This is the representation of this 1 by 3. I'm using 16 bits here to represent this. So, this division, I am converting it into multiplication. So this is sum into 1 by 3. This is 1 by 3. You can check. And again, see, this is, I go for another pipeline register. See, this is a combo logic. This is a combo logic. There is a pipeline register. There is a ridge. This is a pipeline ridge. Again, there is a combo logic. There is a pipeline ridge. In between, I'm inserting all these registers. So this sum underscore div 3 is assigned to average. Okay. So, you can do it in one, each and every clock cycle, so that you will have better throughput. Now let's look at fine.
Sir, how to decide where
for the
pipelining?
assignment?
No, it depends on your requirement, of course. Okay, it depends on your requirement, and based on that the delay and optimization criteria, you can decide all those things, of course. Okay. No, this is again no. We cannot say everything is optimum here. See what exactly happens to your silicon real estate here. So I'm inserting delay. I'm inserting D flip flops here at the cost of silicon real estate. But let's say when this, I'll tell you the concept behind this. The moment this guy completes the task, he is idle now. He is free now. So can I use him again to do some other task? Yes. So I can use the same guy to do some other task. Here also, the moment this is being sampled to queue, this guy is free. This guy is free. Can I use him to do some other task? Yes, that's what you need to think. Yes, the moment this value is being assigned to D out, this guy is free. 1 minute. This guy is free. So the question is, can I use him to do some other task? Now, see, I can ask him to do some other task when once the previous task is over. Same thing I can do with all these guys. So hence throughput is going to improve, but you will have to pay for more silicon real estate. Your throughput is better, but your area is getting increased by, let's say, this many registers. But you can think about it. You can add pipelining depending on your requirement. It all depends on your constraints, of course. Okay.
If we are unable to fix timing, then only we are adding, correct, sir?
Yeah, not exactly like that. Let's say you want to meet your non-functional requirements. Okay, that's with respect to PPAs. Okay, so you will have to play with all these things. Got it? Let's say my timing is not met. Okay, so can I do more tasks? Are you able to understand? In a given time, can I do more tasks, but at the cost of more silicon real estate, of course. That's what is the concept behind this. Okay,
Because right now
just
I'm facing this issue in my project. Like I'm a PD physical design engineer. So right now, like for me, meeting a timing in STA is like closely to
Correct.
impossible. Like we don't have margin. So I have request to RTL team to
correct. Yeah.
pipeline.
Yes,
That's why I
RTL guy
just
should
asked
look
you.
into it. Yeah, RTL guy should look into it. Of course, he has to tweak his RTL to some extent so that he will give you a better bandwidth for you to look at it, of course. Okay.
And sir,
that's
one
possible.
more issue, like for me, for one endpoint, there are 700 start point which is failing. So that is because of pipelining only. Like for one endpoint, if we have 700 start point, like if we fix one endpoint, one start point for that endpoint, 699 start point still is left. So that issue is because of pipelining only, like something happens in pipeline.
Yeah, definitely. Yes.
Okay.
Yeah, definitely. Yeah.
Okay.
Shall I proceed? So, now let's say, and these things are very simple. That's why I'm skipping all these things. Whatever it is there, I have already discussed in my discussion. I think you might remember asynchronous reset in Verilog. I have already discussed, but I have pasted here as a separate PPT. That's it. Okay, whatever is really required, I have already discussed everything. These things are also I have discussed in D flip flop. So with added control signals, preset, clear, and all that. So you can go through it. If you have any doubt, you can ask me when I meet you again. Okay. In the interest of time, I am just trying to skip couple of things, but they are very simple. And if you have understood whatever I have said, you can easily understand those things as well. Now, let's say another important thing, and please go through it. And whenever we meet for the next time, please write it down. And you please don't forget to ask me. I am happy to clarify all your doubts. Okay. So because I will have to look at the FSM also before I wind up today. That's the target for me. That is the deadline for me now. Because so look at this now. I'll give you a concept now. No, it's a very quite interesting scenario. Now, can I extend for another 10 minutes if possible from you? From your end? I am asking your opinion. Now let us say. So let's say the task is like this. Let's say I am giving a clock. Please understand the definition of this system. So I need to generate a control signal that should become 1 whenever 8th clock pulse hits the system, and whenever 12th clock pulse hits the system, it should generate a control signal 1, and in all clock cycles the control should become 0. Okay, so now what should I do now? Let's say the simple logic is 8th clock pulse is like 0, 1, 2, 3, 4, 5, 6, 7. When the count hits 7, that is my 8th clock pulse. When the count hits 11, that is my 12th clock pulse. Yeah, please, can you see here? This is 7, this is 11. 11 means 12th clock cycle. See, in the exam, if I ask, let's say for 12th clock cycle, if I say they write 1100. See, if you write 1100, that gives you 13th clock cycle. It will not give you 12th clock cycle because, so we start from 0, of course. So if you write it as 100, it becomes 8. It gives you 9th clock cycle. See, now look at it. This is LSB. This is MSB. So this is 011. Yeah, just write this. Just write this. I need a lot of time to cover this thing. Okay, yeah, just let me go for this as well. Yeah, see now, see this is, these are LSBs. Let's say this is 1, this is 1. Please understand, this is 1, this is 0. So this is the scenario. So now here, look at it. Here, look at it. Okay. See, this is this one. Please understand this line. This line is this one. This 0 is this one. This one is this one. Now both are, I'm R-ing. Let us say I want it to be what at 13th clock cycle also. Now you will have to write for 1100. How it looks like? How it looks like now? See, you will have one more. Okay. One more, and that also goes as input to this R. Okay, one more and you have here, sorry, the output of that goes as input to this R. So you will have this kind of scenario again. See, it becomes, let's say now this becomes not. You got it? No. Got it? No. Yes or no? See, this is 1. See, this is 1.
Also.
This is 0. Are you understanding? Come on. You followed? Let's say now 0, 1, 1. Let us say this is 0. This is this 0. Okay. Now let us say I want it for 13th clock cycle also. 13th you will get for 1100. How the diagram look? How the logic diagram looks like? Let us say you will have one more AND gate here. The output of that comes as input to this. Okay. And this turns out to be what? 1. See, let us say, see, this is here, it is 0, right? Okay, this is 1. Let's say, see, this is 0 here. Please understand. Okay, so this is 1 here. In our case, this is 1 here. Let's say it goes directly like this. So from here it goes. Again, it is 1, but it is 0 now. See, there is 0 here. This is 0 here. Got it? Is this clear?
For 0, we are using NOT gate.
Yes, yes, for yes. We are using NOT gate. Absolutely. Is it clear, or shall I write it? It becomes clumsy if I write. That's why I'm avoiding it. Is this clear? See? Okay. If
Yes.
not clear, I will repeat again. Just say, see. This is, see, this 0 is, see, this 0. See, from where it is coming. This is my MSB. Please understand. This is my MSB. So if I write 13th clock cycle, it becomes 1100. So it happens to be like this. It happens to be, this is 1. Understood? This is 2. This is, see, here, this guy is sitting here, same line. This becomes inverter. Yes or no? Again, this becomes inverter. Right? Is it clear?
Yes, sir.
Clear, right? So now look at it. See, this is 1. See, this is this one. This is this one. This is this 0. This is this 0. So again, let us say, so depending on this, you must be in a position to write. Say once again, I'll explain this and wind up this example. See this one, let us say this one. See, this is this one, MSB. See, 3 is MSB, just understand. 2 in next bit, this is 0 is LSB. See, this 0 is inverter. This one is this one is this. So if you have 1 more, 2 more, 3 more, you are it. Let's say I have 13th clock, I have 15th clock. You just connect them. Don't worry about number of inputs to R. Okay, that's not your headache. Don't worry. Okay, so now so now, if you look at behavioral description, so what I'm trying to do is, if count and score value is 7, or count and score value is 1011, you got it, no? Means 11. If it is 7 or 11, then my control becomes 1. This is a behavioral description. This is a behavioral description here. Okay, and strictly speaking, it is mixed description. One is data flow and another is behavioral. This is mixed description. So if you want to write, the Verilog code for this functionality, you will have to write like this. Let us say if I ask you to write the structural description, you will have to write D flip-flop separately. You will have to write AND gate separately, 4 input AND gate. You will have to write one inverter separately. You will have to write one OR gate separately, and you have to connect them together. And also you will have to write one adder separately, and you will have to combine them together. You will have to stitch them together. Okay. So now let us say, so let's say how do you define, how do you write a Verilog code for a counter, decade counter? Just 1 minute. Okay, let's say how do you write a Verilog code for a decade counter, a module decade counter? You have output ridge Q, input clock. Very simple thing. You don't have reset also, but you will have to add reset as well. Yeah, so because I just wanted to just go through it, that's all. Not a very good code in terms of synthesizable guidelines, coding guidelines. Okay, so now let us say Q is assigned with, you need to put reset. If you make it reset, it becomes a beautiful code, no doubt. Q is assigned with, let's say, is Q equal to 9? Yeah, please understand, is Q equal to 9? This is the condition. Just 1 minute. Okay, let's say, see, try to understand. So the condition is, this is the condition, is Q equal to 9? If true, see, this Q, please understand, this Q gets the value of 0. If not, Q is not 0. Sorry, Q is not 9. Q is not 9. Let's say Q is 0. What will happen? Next Q becomes Q plus 1. When next clock hits the digital system, it becomes Q plus 1. Now see, is Q, this is my new Q now. This is my new Q. Is this Q 9? No. So what happens? This Q becomes Q plus 1. It becomes 2. So on it will continue. See, is this 9? The question is this 9? Yes. Q is 9. Then next Q becomes this 0. I don't want to increment this. Let's say it becomes 0. It just continues like this. Okay, in many ways you can code it. This is one way in which you can code it. So, okay. Okay, finite state machines. We have 2 types of finite state machines.
So
yeah.
Here it is compare on 9 or 8. 0 to 8 it is considered as a 9, or it will.
No. It is 0 to 9. It is 0 to 9. Okay.
Whatever value we give on that.
Yes. Oh. So there the scenario is different, because when I try to count, I am very keen on the number of counts there. No, here it is, I'm not keen on that. It depends on my rec. That's it. Okay. Is that clear?
Yes.
Yeah.
Thank you.
Yeah, fine. May I know your good name?
Shati.
Okay, fine. So now let us say when you come to FSM, for all controlling stuff, we do use for controlling purpose, we do use state machines. Very basics I would like to touch upon, with some limitations, of course. I may not be able to discuss in detail, and of course, yeah, just please refer more details about it. What best I can do, I will try to do it. So there are two types of machines. One is Murray and another is Millie. Okay. This Murray is, co-founder of Intel, of course. So there is a flip-flop here. There is a combinational logic. So there is output here. There is a output. Okay. See here, the only difference what you can notice here is, okay. So in case of Morris machine and Millie's machine, let's say Morris machine, the output is just a function of state. Look at it. In Morris machine, the output is just a function of state, present state. Now, but in case of Millie machine, the output is a function of state and also function of external input. It's a function of state and also function of external input. Means, let's say the difference here is, please understand, in Moore's machine, I'm trying to make my output independent of input. So, see this independency I'm trying to give, is it, can I exploit this without paying for anything? Let's say any call on this. Let's say if I try to implement some behavior using Millie's model and Moore's model, which one you feel is costly in terms of silicon real estate? Yes, come on. Which one you? Millie? Is this Millie? Sure.
Yes.
Yes.
Yeah. Come on. How many of you say Millie? No. It is it is just for discussion. Don't take it otherwise, of course. If I ask you some doubt, don't take it like I'm trying to check
Murray
or
is
no.
founder of Intel, and who is Miele?
No, Millie, no much information. Sorry, he's one popular guy. He's one guy who has given this concept. But Millie, I don't know much about this. But Murray is, I heard, is co-founder of Intel. He has done something on this as well in the beginning of his career. And also, there is one more thing, I think you heard about JK flip-flop, no? JK, I told you.
Yes, sir.
It is that credit goes to Jacques Kilby of TI as a Nobel laureate, of course. He redefines some of the problems which are there in some memory devices in the beginning. He tries to redefine it, and in his memory it is called as JK flip-flop. Jacques Kilby flip-flop it is. Okay, yeah, fine. So now let us see. This Millie, I don't know if you know, please let me know. See now, let us say, what I just wanted to know here is, as all of you know, FSM coding encoding options, it could be every state could be encoded using 1-0 binary, gray, or any random code one you can think of. I don't look at random now. So binary, it looks like this 00011011. So gray looks like 00011110. 1-0 is only one bit is art at a time, means one at a time. 100010000100001. So this is gray. So which one is good? I think I have discussed in the beginning of my discussion. So this gray, you will see less number of transitions when you move from one clock to next clock. Of course, you don't see many transitions compared to a binary. Of course. Okay. Let's see now. Okay. I'll just go for a very simple model now. Now let us take up one example. Okay. And again, let's say there is one, I think I have 4 minutes left. I think I have 15 minutes left out. Let's say before that, let me just take up something which says present state and next state, let us say. So then the concepts will become very clear to you. Let's see now. Okay. I just take this guy here, let us say. So now let us say, fine. So now, okay. I think you all know JK flip-flop, right? Hope you know JK flip-flop. Okay, let us take JK flip-flop only. Let's say, assume it looks like this. JK flip-flop. I trigger this guy by clock. I have, let us say, 2 inputs. J and K are 2 inputs. Let's say he has Q bar, let's say. What I'm trying to tell, see, the context is not to explain JK flip-flop. This is an opportunity for me to look at JK as well. Very great achievement, of course, when we did not even know what is integrated circuit. He is the guy who said this is how it can be done, just for his work towards integrated circuits. He got a Nobel in 2000. Okay, QJK, but Nobel will not be given for engineering discipline. That is the protocol which they follow, but he got from the domain of physics, of course. It got related to semiconductors and physics, device physics. In that domain, he got Nobel. So now let us say, what I'm trying to tell is, yeah, please understand now. Let's say I apply a clock at t is equal to 0. Please understand. Let's say this is the time t, and assume this is t axis. This is time t equal to 0, let us say. Please understand, this is time t is equal to 0. Now let us say this is time at t is equal to 10. Please understand, t is equal to 10. Next, okay, I think I have gone wrong. Not wrong while writing. I don't want to write like this. Okay, this is, everything is right. This is time 0. Let's say this is time 10. This is time 20, 30. Now see, if I measure the output, please understand, at time 0, if I measure the output at time 0, let us say I call it as present state. So PS, please don't take it as picosecond, and NS I call it as next state. These two are again nanoseconds. Please don't take it like that. NS, if I say in this context, it is next state. So now let's say I measure the output at 10 nanoseconds or 0 nanoseconds. I say it is present state. Let us say I measure the output at the same node, at the same point, at the same node, but at 10 nanoseconds. At 10 nanoseconds or picoseconds. So this is called as next state. Are you able to understand? See, literally what I'm trying to tell you is present state and next state are the values available at the same node, but at a different instant of time. So obviously you see why I'm telling this output can go as input. So there could be a feedback here. No, in any sequential circuit. So let's say now I measure output at 10 time units here, right? Just now I delete couple of things. I measure output at 10 times units. I measure output at 10 time unit. Let's say this could go as input to the same system. And if I measure the output at the same node at 20, if 10 is taken as present state, at 20, whatever you measure, you can take it as next state. Please understand. So this is how present state and next state are defined. Now, this is what I'm going to look at in this discussion. This is the understanding of present state and next state is extremely important. Understood? The understanding of present state and next state is extremely important. You got it now? Now let us say what I'm trying to tell you is, okay, so look at it. Fine. Let's say now, let me move on now. So I need to design a finite state machine to detect a pattern 0101. To detect a pattern 0101. Let's say I need to design a state machine. Let's say the first 0 is coming. This is the first valid bit, let us say 0. So 1 comes. This is not my valid bit. I will stay here and I will wait here. So what is this? This is my output. Whatever I write after slash is output. Whatever I write before slash is my input. This is input. This is output. Okay, see, understand? So if 0 comes, it goes to the next state. See, means with A as present state, B is next state. Please understand. With A as present state, B is next state. Now I'm going to this B state with 0. With A, with input 1, the next state is A. Means present state is same as next state. Now let's say, assume I am here. Assume I am here. What it clearly represents, something which is written in red, means if you look at state B, it represents bit 0 is detected. B is a state which identifies or which says that bit 0 is detected. Now let us say I have detected 0. My next valid bit is supposed to be 1. 0, 1. Let us say if 1 comes, I go to the next state C. If 0 comes again, please understand, if 0 comes again, I remain in the same state. I remain in the same state. I remain in the same state with output 0. let's say still. So the question is, if 0101 sequence is detected, my output should be 1, else my output should be 0. In all other situation, in all other bit patterns, for all other bit patterns, the output should be 0. Only for this bit pattern 0101, my output should be 1. So now look at this. Okay, so now see, I am here now 01. So this C is a state which says 01 is detected. Now if I give 1, yeah, please understand, if I give 1, it is not my valid bit. If I give 1, let me go back here. Let me go back here. Let me go back here. I start again from the beginning. Now if 0, this is the valid bit, I go to the next state, but still my output is 0 because 0101 is not detected. So I go here. So this I'll come to D. D is a state which just detected 010 sequence, but still my output is 0 because 0101 is not yet detected. Please understand. So now I go back. Now I look at this. If 1 is the input, now please understand, if 1 is the input, I'll go back to this state. I'll go back to this state, because this is very optimum in this case, because if I go back to the some of the previous states, it becomes very costly in terms of delay. So now I go back to the 01 state, right? 01 state, and I wait here because 010, 010, this is my valid bit sequence, and it becomes optimum if I go back here 1. If 0 comes, this is not my valid state, I'll go back to this state, this state with output 0. Okay, now you check. You start from any bit sequence to any bit sequence. Let us say, see, I start from 1 here, 1 complete cycle you have to consider. 1 again, this is 0, this is 1, this is 0, this is 1. See, this is okay. Hope you understand. See, look at it. See, I start from here 1, this 0. Okay, then this 1 I consider, this 0 I consider. Again, no problem. What is the output? This output you have to consider, this 0. Again, let us say. So is this true for 0101 sequence? Let us see. Just say. No, I think you will have to put some effort to understand this. Okay, see, now let us say I have 0, here 1, I have 0, I have 1. My output is 1. Okay, right? And again, let us say I start from here. Look at it. Again, I can start from here. Look at it. So I start from here, not this 0. This 0, 1. Okay, this 0, this 1, this 0, this 1. It's giving me 1. For rest of the cases, you will get 0 only. Okay, just see, that is clearly mentioned here. See, 0 I give, 1 I give, 0 I give, 1 I give. What is the output? It is 1. 0 0 1 0. What is that output I am getting? 0 0, because I am not getting 0101 sequence. See now here. So here 1, it is 0101 is detecting, I'm getting 1. Again 0101 is detected, I'm getting 1. See this, please understand, this 1 is common to the previous sequence and present sequence. Hence it is called as overlapping. So I said overlapping is allowed. Hence I say overlapping is allowed. Now let us look at Verilog part of it. So now let's say I'll go for, there are ways of modeling it. I'll just go for, very simple model now, let us say. But you need to remember this. If you remember, it will be very easy. Okay. I just look at something which, okay. Yeah, this is quite attractive. Yeah.
Sorry for interrupt, but can we say that whatever the last bit of the pattern, it will be the output?
Last bit of the pattern, if you use, any style you use, any design, if it is optimum, definitely it can be taken. But last bit doesn't mean that it is going to be the output. No, it depends on your requirement. If you feel last bit is supposed to be your output as well, accordingly you can design it. Okay, it depends on your requirement. That's it. Okay, fine. No, it's basically used in communication issues, of course, because I just wanted to look at sequence of bits according to my requirement. Okay, so now let's say for the same behavior, how can I write a RTL code? Let's say you look at it, clock reset, reset, X is input and Z is output. Let's say all these are defined here, please understand. So now, as I said, I have present state and next state, I declare them as registers, and Z also I declare it as a register. And the states, ABCD, if you look at, yeah, please understand, I have ABCD. No digital circuit can understand the meaning of ABCD. I need to encode that using binary values. So that is why the option in Verilog is parameter. Parameter A is 00, B is 01, C is 10, D is 11. It's your wish. A 00, B can be 01, C can be 11, D can be 10. No problem. Okay. So now always at passage clock or negate reset begin. If not reset, let's say state is A, means if reset N, let's say if reset N, let's say, so the initial reset state is A. Okay, if reset is 0, please understand it is active low reset. You can go for active high reset, it's your wish. So negate G is used, that's why active low reset I'm taking it. So active low reset, if reset N is 0, okay, my initial state is A, else my state is else. Okay, just look at this, else my state is any doubts here? Yeah, come on, any doubts here? Yeah, this is the simple model. All the models are perfectly fine, but one uses function, probably another uses procedure, something like that, but all are functionally same. This is the simplest model. Okay, so yeah, any doubts? So always at passage clock or negate reset, let us say, what I'm trying to say is, if not reset, present state is A, else present state is next state. So what does it really mean? Please understand. This is the present state, this is the next state. Now, after one clock pulse, this becomes my present state. This present state was my previous next state. Please understand. This I will have to code it. So now with this as present state, this is my next state. When I come here in the next clock cycle, this becomes my present state, this becomes my next state. Means my next state will become present state after the occurrence of every clock pulse. This is what I am supposed to mention here. Look at it. That's what I am doing here. If not reset, present state is A, else what? Next state becomes present state. This is what I am doing. So that's how you should understand. Now, see, this is, if you know the state transition according to your requirement, you can write it. Yeah, please understand. So now let us say, so what I am doing, let's say I'm starting with, can I take 2-3 minutes extra? Is that allowed? Yeah, maybe if required, I will take, otherwise I will try to complete. Let's say now. So I think I cannot, yeah, see, let's say this is my reset state. This is my A. So this is my A, please understand. So if X means, if X is 1, okay, if X is 1, what is my next state? Let us say if X is 1, my next state is 1. Okay, see, and if X is 1, look at this. If X is 1, my output is 0. See, look at this also. For state transition, look at this. For output, you look at this. This always for output. This always for state transition. State transition. Okay, now, so if X is 1, this is the case. Else, if X is 0, this is how I come. If X is 0, next state is B. Please understand, next state is B. Now I am here. Next state is B. Now with B as present state, please, this is with A as present state. With B as present state, if X is 1, next state is C. Please understand. If X is 1, next state is C. See, what you have to do, you have this already with you. You have this with you, accordingly you have to write this. That's what you are supposed to do. So B, else next state is B. See, else next state is B, means if it is 0. See, with B, look at it, with B the output is 0. With C, this is this. With the C, let us say with C as the present state, Is this clear?
So when the next state is from B, when the next state is C,
Yeah,
how
see,
it is
yeah,
coming back?
1 minute, 1 minute, 1 minute, 1 minute. So I think 1 minute. I think I directly went to C. Let me just check with the C0, X1, C0. No, sorry, this goes to D. I'm sorry, this goes to D. This is your doubt? Was this your doubt or
No,
not?
no. My
Okay.
doubt is when
I think
the
this
next
is not
state.
required. This yeah.
Oh,
Tell
so
me.
this is not required. So my doubt was like that only. So when we are at the next state C, then how the state is getting changed to B again? That is what my doubt.
1 minute, let's say. Yeah, just 1 minute. Let me just control 1 minute. Let me paste it in Word probably. Just see. I think it becomes 1 minute. Let us say. See now, let us say. Let's say the syntax is present state A. It is like this, right? Comma. There is a case statement. Comma. If look at it. If X means X is 1. Next state is, let's say, NSI right here. Next state is A. Else means X 0. What is my next state? My next state is B. This is what is written there. That's it. Next, with B as present state, you write like this: B. If X is 1, NS is, I think there it is written as next state. NS is what? C. Else what? If X is 0 with B as present state, else NS is what? B. Is this clear now? Did I clear your doubt? Probably I think I have cleared your doubt.
Yes.
Yes? Is your doubt clear?
Yes,
yeah.
sir.
So now similarly with C it happens. So if X, please understand, if X with C as the present state, X is 1 with C, if X is 1, what is the next state? A is the next state. NS is A, else what? With 0, what is the next state? Come on, tell me. NS is B. Now let us say there is one more always where I have output case A. It is similar to case A. I think I have written if let's say X equal to 1, let us say, as I said, NS is A. You got it? No. Else NS is B. Here you can write output here. See, you can write output in this case. Okay, just see.
So how we are capturing the output by the state machine? We are just changing the
no that you will have to that you will have to design. When you design this accordingly, you have to code it. You will have to design this.
This is the algorithm.
Yes, it is an algorithm. You are absolutely right. It is an algorithm. For that algorithm, you will have to code it. This is the coding part I am discussing. 1 minute. So, because I cannot sync both, that's the problem. I'm trying to, there is some problem with my laptop. I'm trying to put it on Word. So it would have become a bit clear. So now look at it. If X, okay, let's say, okay. Now with respect to output, let us say, if X equal to 1, let's say, with A as the present state, please see, with A as the present state, if X equal to 1, what is the output? If X equal to 1, let's say, just wait. I'll complete this and wind up just. So A is the present state. Let's say if X, if I write, if X means X is 1, what is output? Z equal to, come on, Z is 0. I'm not following the syntax. Else, what? Else, Z is what? Else means if X is 0, what is Z? This one, Z is 0. Now with B as present state, please understand. Now you come here. If X is 1,
Okay,
If
so
X,
our output is getting
what is
sent
this? Output is 0. Output is 0. Z is 0. Else what is that? Z is if X here X, else what? If 0 output is what?
1.
0. No, 0. Here this 0. Now with C, if X, same thing you will have to repeat. If X here, if X is 1, see with C, if X is 1, what is this output? See, only 0. This is 0. Else the output is, see, if X is 1, it is 0. Else also it is 0. Z is 0. You can write. The tool will optimize it. You don't worry about it. Or if you want, you can, you can optimize manually on your own before you code it. That's also possible. With the D, if X, what is this? With the D as the present state. If X, what is output? Come on, tell me. If X, Z equal to, what is output? This one, Z equal to 1. Else, what is that? What is that?
0.
If X equal to 0, this 0, right? 0. That's it. See, this always for output and the previous always for next state transition. That's it. Now, like this, you must be in a position to code any FSM. You must be in a position to code any FSM. So, any doubt here? Any doubt? If you have any
sir,
doubt,
you
please ask me.
told,
Come on.
no, you told like if C
Yeah.
is the present state, then A will be the next state.
Correct.
So how it become?
Yeah, 1 minute. Let me.
D should be.
Yeah. Wait. Let's say now at first clock. Let us say. Assume I am applying the clock beginning. 1 minute. Yeah. Initially, I'm applying a clock. Okay. Now, can I say this is my present state? I'm starting with this. Is this my present state?
Yes.
Now, I apply one clock. Okay. So it goes through this transition. It goes through this transition B. Now, please understand, with this as present state, this is my next state. Is this clear? This is my
Yes.
next state. Now, is that over? Now, let us say first clock is over. Assume, second clock is hitting the system now. Second clock is coming to my system. Now I am in state B. Is that right?
Yes.
Yes. Now, see, in this state B, right? See, this state B was my next state in the previous clock cycle. Am I right?
Yes.
Now, if I come to this current clock cycle, is this B is my present state?
Yes.
Yeah.
Present
See,
state.
the one which was next state in the previous clock cycle becomes the present state in the current clock cycle. Are you able to understand?
Yes. Yes.
As and when clock hits, this happens everywhere. So now this becomes present state, this becomes next state. Are you able to understand in the next clock cycle?
Yes.
Now when I come to C, again when I come to C, this C was the next state when I was in B as present state. Now when I come to C, C becomes present state, but C was my next state in the previous clock cycle. So that is why as and when new clock hits, as and when clock is hitting the system, next state always becomes present state. That you should include in one of the modeling style. Otherwise it doesn't work. You'll have to pass this information. Otherwise proper transition will not happen. In one coding style, there are various ways in which you can code it. The simplest one and easy to understand I have discussed. Now I think I have given all other codes. They're also functionally all right, but they uses different styles. Is that clear to all of you? Yeah.
Yes.
Sir,
Yeah.
sir, the pattern which we are detecting like 0, 1, 0, 1. So, sir, we are considering A, B, C, and D. That pattern,
okay. Yes,
like that in complementary like that. And according to the input at A, we are seeing like 1/0. These are the inputs. So accordingly, we are moving in that direction.
correct.
Am I right?
Correct.
And so one more thing, sir. This written in the red color, sir, what that means? This is the pattern we are detecting, or just we are giving the input accordingly which we are moving?
No, see, this is the input. Both are right. This is the input you are giving. I'm giving this input. It is a serial input. Only one bit is entering this complete system. It is serially. I'm feeding this bit. You got it, no? when this bit, let's say first I feed 0, next I feed 1, next I feed 0, next I feed 1. Are you able to understand?
Yes.
See, now let us say if I receive these bits in this sequence, let us say first I feed 1. You please understand, first I feed this 1. Next I feed this 0. Next I feed this 1. Next I feed this 0. When I get this sequence, let's say, look at this, one minute. I just copy and paste this. I think it will be very clear to you. Just wait.
Sir, why this sequence we are feeding? We are giving the input to detect the pattern
Yes,
0101. So, sir,
absolutely. Absolutely, we are giving inputs. Here, see, this is my input X. See, this is 0101 is my input X only.
Okay.
Yeah, is this clear?
Yeah.
Any doubts still?
No.
Input X, serially I'm giving 0, 1, 0, 1, like that it is giving. Like that, okay. I'm providing input. And I'm just see, my task is if 0101 pattern is detected, my output should become 1. If the pattern is other than this, my output should become 0. For this task, I am implementing a digital system which can do this job. That's it.
Yeah, okay.
Okay, clear?
Okay. Yeah.
Yeah. Shall I wind up this? Or if you have any doubts, I'm happy to clear all your doubts. I think probably I'll be meeting maybe on session 8, probably review, maybe, right? So, yeah. So if you have any queries, I would like to address those queries in my next session. Okay. Yeah. So thank you. Bye.